In the previous video, we had looked at finding the center of mass for a piecewise region. In this video, we want to look at finding the center of mass for a continuous region and taking our summations and converting those into integrations. So here on the iPad screen, you can see a region that is continuously defined. The curve that we're working with here is y equals x squared, or f of x equals x squared. So we will try to figure out where the center of mass of this is. First, we'll look at it theoretically, and then we'll actually do the calculations. So from the last video that we had, we may have divided this region. Doesn't need to be a specific function, but we had divided a region into multiple subintervals. Let's just do 4 subintervals here. And why don't we look at a sort of a midpoint sum of those? So if I look at where the midpoint heights are for each of these subintervals, there would be at the halfway points of each of these. And if I wanted to find the average value of x for each of the x values that I would pick, I would want to use the amount of area over that x value. So in this particular example, 0.5 would be x1, 1.5, whoops, let me make that a 1, 1.5 would be x2, 2.5 would be x3, and 3.5 would be x4. And then we have a corresponding height for each one of those. So the height of the first subinterval is here, somewhere around 0.6. The second height, so I said the height right in the middle, be somewhere around 1.3, and then the third height would be somewhere around 1.5, and the last height would be probably around 1.8 or so. In general, we can write this that if we were trying to find the average position of x, we would say that x average is equal to the summation of the x of I value times, I'm going to use delta A of I this time. And in order to get the average, we then have to divide out the total area. So the amount of area stacked over each of the x values tells us how much to weight that x value. So in the summation, the x values where the area is larger, we will end up counting those more as we go to find the average. So back to this calculation, the key would now be to figure out what is the delta A that we're working with. Okay, so when we're trying to find the x, we would have a delta A. Okay, and to get the delta A value, we would have to consider that for each of these, we're going to have a height times a width. And in order to get the height, we're going to want to always take, since it's a vertically aligned region, we will want to take the top minus the bottom of the region. And we'll multiply that times the width. In this case, the top of the region just happens to be, we'll just generically say it's f of x, and the bottom of the region is at 0. So that's my height times delta x. So I can fill in that if I want to for the formula, if I want to find the average value of x, I could say that x average is equal to the summation of x of I times, instead of delta A of I could put in that this is f of x of I times delta x. And then in the denominator, I would have the summation just of the f of x of i's times delta x. Now, when you see that, I think it's pretty clear how we could turn that into integration. First of all, from what we know about Riemann sums, we know that using more subintervals is better. So rather than using only 4 subintervals here, I easily could have stretched this out and divided each one of these in half. And if I have more subintervals, I'm likely to get closer to the actual area. And if we use an infinite number of subintervals, the summation becomes an integration. So if I want to convert this into an integration, I simply have to consider what happens in the limit that n goes to infinity. So let me try to scroll up here. In the limit that n approaches infinity, the average value of x would become an integral of x times f of x dx all over the integral of f of x dx. And these would be from a to b, for both of them, to define the region. And so this formula would turn our summation into integration and allow us to use slices that are infinitely thin.